Welcome on board, Wanderers. You know that feeling when you're absolutely certain about something and then someone shows you proof that you've been wrong your whole life? That moment when the floor drops out from under everything you thought you knew. We're going to do that to you right now because the universe isn't behaving the way it should. And the more we learn and know about it, the stranger things get. The weirder the implications become, the more unsettling the questions that keep scientists awake at all night. Let me paint you a picture. Imagine you're standing in a room where the walls are moving away from you, not dramatically, not all at once, but slowly, imperceptibly, the space between you and everything else is growing. Now imagine you can't feel it happening. You can't see it with your naked eye, but it's there, measurable, real, undeniable. That's where we are right now. That's where we've always been. The universe is expanding. But here's where it gets unsettling. It's not just expanding, it's accelerating, speeding up, like a car whose driver keeps pressing harder on the gas pedal, even though there's no road ahead, no destination in sight, just an infinite stretch of cosmic highway extending into nothing. And we have absolutely no idea why. Let's rewind for a second. Because this story doesn't start with some abstract equation or theoretical prediction. It starts with light, with colour, with something so simple a child could understand it, yet so profound it rewrote our entire understanding of existence. Picture this. The 1920s. Jazz is everywhere. Prohibition is in full swing. And a guy named Edwin Hubble is sitting in an observatory on Mount Wilson in California, staring through one of the most powerful telescopes humanity had ever built. Night after night, he's photographing galaxies, these fuzzy smudges of light scattered across the cosmic canvas. And he's measuring something strange. The light from these galaxies isn't quite the right color. Now, Hubble knew his physics. He knew that when something moves away from you, its light stretches, gets redder. It's the same principle that makes an ambulance siren drop in pitch as it speeds away from you. The Doppler effect, but with light instead of sound. And every single galaxy he looked at, redder than it should be. Every single one. At first, you might think, what? Okay, so some galaxies are moving away from us, so what? But here's the kicker, they weren't just moving away. The farther away a galaxy was, the faster. It was receding. There was a relationship, a pattern, a cosmic speed limit that seemed to scale with distance. Think about what that means for a second. Really think about it. If everything is moving away from everything else, and the farther things are, the faster they're retreating, then at some point in the past, everything must have been closer together, much closer, impossibly close. Hubble had stumbled onto something that would fundamentally alter how we see our place in the cosmos. The universe wasn't static, wasn't eternal and unchanging like people had assumed for millennia. It was dynamic, growing, evolving. It had a history. But we're getting ahead of ourselves. Let's dig into how Hubble actually figured this out, because the detective work here is absolutely fascinating. See, when you look at light from a galaxy, you're not just seeing a uniform glow, you're seeing a spectrum, a rainbow of colours, each corresponding to different wavelengths of light. And embedded in that spectrum are these dark lines, absorption lines they're called. They appear because atoms in the galaxy absorb specific wavelengths of light, leaving gaps in the spectrum like missing teeth in a smile. Different elements absorb different wavelengths. Hydrogen leaves its signature. Helium leaves another. It's like a fingerprint, unique and identifiable. Now here's the brilliant part. We know what those fingerprints should look like. we can create those same elements in a lab here on Earth and measure their absorption lines. We know exactly where those dark lines should appear in the spectrum. But when Hubble looked at distant galaxies, those lines weren't where they were supposed to be. They were shifted, moved toward the red end of the spectrum. And not just a little bit. Some galaxies showed massive red shifts, their spectral lines displaced so far that the whole pattern was nearly unrecognizable. The math was simple, brutal even. The farther the galaxy, the greater the redshift. The greater the redshift, the faster it was moving away. Distance equals velocity times time. Hubble plotted his observations on a graph, distance on one axis, velocity on the other. And what emerged was a straight line. A perfect, undeniable linear relationship that would later be called Hubble's law. For every megaparsec of distance, galaxies were receding at about 70 kilometers per second faster. Megaparsec by megaparsec, the universe was stretching, expanding, growing like some cosmic organism that had no intention of slowing down. But why? That question haunted physicists, because according to everything we knew about gravity, the expansion should be slowing down. Matter attracts matter, gravity pulls. Every galaxy tugging on every other galaxy should act like a brake on the cosmic expansion. Over billions of years, that gravitational attraction should slow things down, maybe even reverse them, pulling everything back together in a catastrophic collapse. That's what made sense. That's what the equations predicted. That's what should have been happening, except it wasn't. Decades passed, technology improved, telescopes got bigger, more sensitive. We launched observatories into space above the distorting effects of Earth's atmosphere. We developed new techniques for measuring cosmic distances, new ways to peer deeper into the universe's past. And in the 1990s, two independent teams of astronomers set out to measure exactly how much the expansion was slowing down. They weren't trying to prove anything revolutionary. They were just trying to nail down the numbers, to quantify the deceleration, to put precise figures on something everyone assumed was happening. They used supernovae, specifically type Ia supernovae, which are like cosmic lighthouses. These explosions happen when a white dwarf star accumulates too much mass from a companion star and goes critical, detonating with such consistent brightness that astronomers can use them as standard candles to measure cosmic distances. The logic was straightforward. Observe distant supernovae, measure their redshift to determine how fast they're moving away, measure their brightness to determine how far away they are, and plot the relationship. If the expansion was slowing down like gravity predicted, distant supernovae would be closer than their redshift suggested. The universe would have been expanding faster in the past, meaning objects at a given distance would have taken less time to reach that distance. They gathered data, they checked their instruments, they ran the numbers, and then they checked them again because something was wrong. The distant supernovae weren't too close, they were too far, way too far. The expansion wasn't slowing down, it was speeding up. Let that sink in for a moment. The universe, against every expectation, against every prediction of gravitational theory, was accelerating, expanding faster now than it was billions of years ago, like someone had cut the brake lines on a car that was already rolling downhill and then somehow managed to put it in a lower gear. The announcement came in 1998. The room of astronomers where the findings were first presented reportedly went dead silent. Because this wasn't just surprising, it was world-shattering. It violated our fundamental understanding of how the universe should behave. Gravity attracts. That's what it does. That's all it does. It pulls things together. There's no repulsive gravity, no anti-gravity force in Einstein's equations. Matter curves space-time, and objects follow those curves, falling toward concentrations of mass. So what could possibly be pushing the universe apart? The answer, in the most frustrating way possible, is we have no idea. We call it dark energy, but that name is just a placeholder, a label for our ignorance. It's like calling thunder loud sky noise before you understand the physics of lightning. Technically accurate, but revealing nothing about what's actually going on. Here's what we do know. Dark energy makes up roughly 68% of everything in the universe. Not matter, not radiation. Something else entirely. Something that doesn't clump together like matter does, doesn't dilute as space expands like radiation does. It's smoothly distributed throughout space, and it has a bizarre property called negative pressure. Negative pressure. Think about that phrase. Pressure pushes things apart, right? Air pressure inflates a balloon. Water pressure can split rock, but negative pressure, that's something different. In Einstein's equations, negative pressure acts like a kind of anti-gravity, repulsive force that pushes space apart. And it's everywhere. Every cubic meter of space contains this dark energy. As the universe expands and creates more space, it creates more dark energy. Unlike matter, which gets more spread out and diluted as space grows, dark energy maintains constant density, which means the more the universe expands, the more dark energy there is, and the stronger its repulsive effect becomes. It's a runaway process, a cosmic feedback loop. Expansion creates space. Space contains dark energy. Dark energy drives more expansion, which creates more space, which contains more dark energy, which drives more expansion forever, or at least as far into the future as we can calculate. Now, some of you might be thinking, wait, couldn't this just be a mistake? Maybe we're measuring something wrong. Maybe there's a simpler explanation. That's exactly what the scientific community thought at first. The initial reaction to the discovery wasn't celebration. It was skepticism, disbelief, a collective check your work that lasted for years. But the data kept coming in, more supernovae, better measurements, different teams using different methods, all arriving at the same conclusion. The cosmic microwave background radiation, the afterglow of the Big Bang itself, showed patterns consistent with accelerated expansion. Large-scale surveys mapping millions of galaxies revealed distribution patterns that only made sense if dark energy was real. The evidence became overwhelming. In 2011, the Nobel Prize in Physics was awarded to the leaders of those two supernova teams. Not because they'd explained dark energy, not because they'd solved the mystery, but because they'd discovered that the mystery existed in the first place. And what a mystery it is, because here's the thing, we can describe what dark energy does. We can measure its effects with remarkable precision. We can plug it into our equations and make predictions that match observations to incredible accuracy. But we cannot explain what it is, where it comes from, why it exists. Some physicists think it might be a property of space itself. That empty space isn't really empty, but seethes with quantum fluctuations, virtual particles popping in and out of existence, and that somehow these fluctuations create a kind of vacuum energy that manifests as dark energy. Except when you actually calculate how much energy those quantum fluctuations should produce, you get a number that's 10 to the power of 120 times larger than what we observe. That's not just wrong, that's spectacularly, monumentally, embarrassingly wrong. It's been called the worst prediction in the history of physics. Others propose that maybe gravity itself works differently on cosmic scales than we think. That Einstein's general relativity, which has passed every test we've thrown at it for over a century, need modification when applied to the entire universe. Modified gravity theories proliferate in the literature, each attempting to explain acceleration without invoking dark energy. None of them work perfectly, all of them have problems. Some suggest dark energy might not be constant, that it could change over time, strengthen or weaken, possibly even reverse. We call these theories quintessence, after the fifth element of ancient philosophy. The idea is that dark energy is actually a dynamic field pervading space, something that evolves as the universe ages. If that's true, the fate of the universe becomes even more uncertain. Depending on how quintessence behaves, we could be heading toward scenarios with names like Big Freeze, Big Rip, or Big Crunch, each one stranger and more unsettling than the last. Let me walk you through what we think might happen, what the current observations suggest about the ultimate fate of everything. Right now, galaxies beyond our local group, the small cluster of galaxies held together by mutual gravity, are moving away from us. As space expands, that recession accelerates. Eventually, billions of years from now, those galaxies will be moving away so fast that their light will never reach us. They'll cross what's called the cosmic event horizon, disappearing from view forever. The observable universe will shrink. Not physically, we're not going anywhere, but the amount of the universe we can see, the portion of space whose light can reach us, will contract. Galaxies will wink out one by one, their light stretched to such long wavelengths that they become invisible until finally all that remains visible are the few dozen galaxies in our local group. Future astronomers, trillions of years from now, will look out at a night sky containing only those nearby galaxies. Everything else, the vast cosmic web, billions of galaxies we see today, will be gone, vanished beyond the horizon. And those future astronomers will have no way of knowing it ever existed. They'll look at the universe and conclude that they live in a small island of galaxies surrounded by infinite emptiness. They won't have evidence for the Big Bang because the cosmic microwave background radiation will have been stretched to wavelengths too long to detect. They won't see distant galaxies receding because there won't be any distant galaxies to see. They'll be wrong about the universe. Fundamentally wrong, through no fault of their own, simply because the universe has expanded to the point where the evidence has literally moved beyond their reach. Which raises an uncomfortable question. What are we wrong about? What evidence has already slipped beyond our cosmic horizon, leaving us ignorant of truths we can never recover? But let's keep going forward. Let's imagine the universe continues expanding, accelerating for trillions upon trillions of years. Stars burn out. New star formation slows and eventually stops as galaxies exhaust their gas supplies. One by one, the lights go out. Red dwarfs, the smallest and longest-lived stars, will continue burning for tens of trillions of years, but eventually, even they'll fade. The universe goes dark. Matter itself begins to decay. Protons, which we think might be stable, might not be. They might have a half-life measured in something like 10 to the power of 36 years. Well, we've never observed proton decay, but that doesn't mean it can't happen. If it does, then over time scales so vast they beggar imagination. Even atoms will fall apart. Black holes, the final repositories of matter, the ultimate endpoints of gravitational collapse, will evaporate through Hawking radiation. Slowly, incomprehensibly slowly. A stellar mass black hole might take 10 to the power of 67 years to evaporate. A supermassive black hole at the center of a galaxy, 10 to the power of 100 years. But eventually they'll all evaporate. And when the last black hole radiates away its final quantum of energy, what's left? Nothing, or almost nothing. Just space itself. Still expanding, still accelerating, growing emptier and colder and darker with each passing eon. Particles so far apart that they'll never interact. Energy diluted to the point of meaninglessness. Temperature approaching absolute zero. Heat, death, the big freeze. The universe doesn't end with a bang or a whimper. It just fades. Becomes increasingly dilute, increasingly cold, increasingly empty forever. That's the future dark energy seems to be writing for us, unless it's not. Because here's the truly maddening part. We don't actually know if dark energy is constant. What if it's getting stronger? What if that negative pressure, that repulsive effect, increases over time? Then we get something called the Big Rip. Imagine dark energy growing so powerful that it overwhelms not just gravity on cosmic scales, but gravity everywhere. First, it would tear apart galaxy clusters, then galaxies themselves, then solar systems, then planets, then molecules, then atoms, then atomic nuclei. Eventually, if dark energy continued strengthening, even space-time itself would be shredded, the very fabric of reality torn apart in a catastrophic unraveling that would happen everywhere simultaneously. One moment, the universe exists. The next moment, nothing. Not even space-time. Current observations suggest this isn't happening. The data indicates dark energy has been roughly constant over cosmic history, but roughly constant isn't the same as definitely constant, and we've only been able to probe the last few billion years of cosmic history with any precision. And what if we're wrong about all of it? What if dark energy is somehow an illusion, a misinterpretation of data, and the real explanation is something we haven't even thought of yet? That possibility keeps cosmologists up at night. Because science proceeds by building models that match observations, but multiple models can sometimes match the same data, especially when that data is incomplete. We're pattern matching with incomplete information, trying to infer the rules of a game when we can only see part of the board. Think about ancient astronomers trying to explain the motion of planets. They saw planets move across the sky, sometimes forward, sometimes backward in retrograde motion. They built elaborate models with epicycles, circles within circles, mathematical frameworks that could predict planetary positions with decent accuracy. They were wrong, not because their math was bad or their observations were sloppy, but because they had the wrong fundamental picture. They thought Earth was the center of everything. Once you shift your perspective, once you put the sun at the center, the epicycles vanish. The model simplifies, the truth emerges. Are we making the same mistake? Do we have the wrong fundamental picture of what's happening? Some researchers wonder if the universe isn't actually homogeneous. The cosmological principle, the assumption that the universe looks roughly the same in all directions and from all locations, is a cornerstone of modern cosmology. But what if we live in a special place? A low-density bubble in an otherwise denser universe? If that's true, expansion could appear to be accelerating from our vantage point, even without dark energy. It would just be a perspectival effect and an artifact of our location. Most cosmologists reject this idea because it would require us to occupy a very special, very unlikely position in the universe. And historically, every time humans have assumed we're in a special place, the universe at the center of things, we've been wrong. But unlikely isn't the same as impossible. Others propose that maybe our understanding of gravity breaks down on very large scales. General relativity works perfectly for solar systems, for galaxies, even for galaxy clusters, but the entire observable universe, that's a regime we can't test in any controlled way. We have one universe, we can't run experiments on it, we can only observe what it does. Modified gravity theories attempt to tweak Einstein's equations in ways that might explain cosmic acceleration without dark energy. Some of these theories predict subtle differences in how galaxies cluster, how light bends around massive objects, how gravitational waves propagate through space. Testing these theories is extraordinarily difficult. The effects are subtle, the scales are vast, but projects are underway. New telescopes, new surveys, new gravitational wave detectors, each one probing a slightly different aspect of gravity's behavior, looking for cracks in the theoretical foundation. And then there's the simulation hypothesis. Stay with me here because this gets weird. What if our universe is a simulation, a computational construct running on some substrate we can't perceive or interact with? In that case, dark energy might be a computational artifact, a rounding error, a feature of how the simulation implements physics rather than a fundamental property of reality. You might laugh, you might dismiss this as science fiction, but serious physicists take this possibility seriously enough to write papers about it. Not because there's evidence for it, but because it's logically possible and because it would explain certain otherwise inexplicable features of our universe, like fine-tuning, the cosmological constant, the vacuum energy that might be dark energy, has a value that seems impossibly, ridiculously fine-tuned. If it were slightly larger, the universe would have expanded too quickly for galaxies to form. Slightly smaller, and the universe might have recollapsed before stars could ignite. The value sits in a narrow range that allows for complex structure, for stars and planets and life. Either we're extraordinarily lucky, or there's some mechanism that sets the cosmological constant to this value, or we're in a simulation deliberately configured to allow for our existence. None of these options are particularly satisfying, which brings us full circle back to the fundamental question. Is our universe still expanding? Yes. Unequivocally, undeniably, yes. The evidence is overwhelming. Redshift measurements from millions of galaxies, the cosmic microwave background, large-scale structure, multiple independent lines of evidence all pointing to the same conclusion. But the deeper question, the one that really matters, is why? Why is it expanding? What is dark energy? Where does it come from? Why does it have the value it does? Will it continue forever? We don't know, and that's terrifying, exhilarating, humbling, because here we are, 7.8 billion humans on a small rocky planet, orbiting an unremarkable star in the outer suburbs of an average galaxy, and we've managed to figure out that the universe is expanding, that it's been expanding for nearly 14 billion years, that it's accelerating, that 68% of the cosmic energy budget is something we cannot see, cannot touch, cannot directly detect. We've built telescopes that can observe galaxies billions of light years away. We've measured the afterglow of the Big Bang to incredible precision. We've detected gravitational waves from colliding black holes. We've photographed the event horizon of a supermassive black hole at the center of a distant galaxy. And yet the universe keeps most of its secrets, holds them close, dares us to dig deeper, look harder, think more creatively. Every answer we find spawns new questions. Every mystery we solve reveals deeper mysteries lurking beneath. It's like peeling an onion, except the onion is infinite, and every layer is stranger than the last. Maybe that's the point. Maybe the universe isn't meant to be fully understood. Maybe the pursuit of understanding, the endless quest to know more, to see farther, to comprehend deeper. Maybe that's what gives meaning to our brief existence, because we won't be around to see the end, whether it's heat death or big rip or something we haven't imagined. The universe's ultimate fate will play out on timescales so vast that the entirety of human history, from the first stone tools to whatever we become millions of years from now, is less than a blink. But we can think about it, we can model it, we can peer backward in time to the moment of the Big Bang and forward to the far future when the last stars fade. We're made of atoms forged in the hearts of ancient stars. Carbon, nitrogen, oxygen, iron, every element heavier than helium created in stellar furnaces or supernova explosions. We are, quite literally, stardust. The universe experiencing itself. Matter organized into patterns complex enough to ask questions about its own existence. And the universe is expanding around us, carrying galaxies away into darkness, accelerating toward a future we can barely glimpse. Somewhere out there, on a planet circling a star in a galaxy we can see through our telescopes, maybe someone else is asking the same questions. Looking up at their night sky, measuring redshifts, building theories, grappling with the same cosmic mysteries. Will they figure it out before we do? Will they solve dark energy while we're still guessing? Or will both our civilizations and countless others scattered across the cosmos all struggle with these questions until the universe itself forgets the answers? The expansion continues. It doesn't care whether we understand it. It doesn't pause to let us catch up. Every second, space stretches, galaxies recede, the cosmic horizon shrinks, and here we stand, small and temporary and absurdly ambitious, trying to understand it all, trying to make sense of a universe that owes us nothing, explains nothing, and yet reveals itself piece by piece to anyone patient enough to look. The universe is expanding, it's accelerating. Dark energy pushes it apart with increasing force, driving toward a future that grows dimmer and colder with each passing eon. And we're here, right now, in this brief window of cosmic history, where stars still shine, where galaxies are still visible, where evidence of the Big Bang hasn't been stretched beyond detection. We're here to witness it, to measure it, to wonder about it. Maybe that's enough, or maybe, just maybe, we'll figure it out, crack the code, understand dark energy, peer behind the curtain and finally see what's really going on. Until then, the universe expands and we watch and wonder and reach for answers that dance just beyond our grasp, in the dark spaces between the stars. The thing is, we're not just passive observers in this cosmic drama, we're active participants, even if our role seems microscopically small. Every telescope we build, every detector we activate, every equation we solve brings us incrementally closer to understanding. Or at least that's what we tell ourselves. But what if understanding isn't actually possible? What if the universe operates on principles so far beyond human cognition that we're like ants trying to grasp quantum mechanics? We can measure the effects, sure, we can catalogue observations, but gen comprehension, that might be forever out of reach. Consider this, our brains evolved to help us survive on the African savanna, to recognize patterns in animal behavior, to avoid predators, to find food and shelter. Nothing about natural selection optimized our neural architecture for understanding cosmic expansion or quantum field theory or the nature of dark energy. Yet somehow we can, Somehow these 3 pounds of electrochemical jelly sitting in our skulls can contemplate the fate of the universe, can build mathematical frameworks that describe reality with stunning precision, can peer back to moments after the Big Bang and forward to the heat death of everything. That's either a cosmic accident or profoundly significant. Maybe both. The accelerating expansion poses another uncomfortable question that doesn't get talked about enough. What does it mean for the future of intelligence in the universe? Think about it. If conscious, intelligent beings arise from complex arrangements of matter, and if dark energy continues to dilute and separate matter across ever-increasing distances, then the future of intelligence looks pretty bleak. Right now, we can theoretically travel to other stars. It would take thousands of years with current technology, but it's not physically impossible. We could in principle spread throughout the Milky Way, given enough time and resources. Other galaxies in our local group, those are harder but still potentially reachable. But galaxies beyond the local group, already moving away faster than we could ever travel, even at the speed of light. Dark energy has effectively walled us in. We live in a cosmic prison, bounded not by bars but by expanding space itself. And it gets worse, much worse. As expansion accelerates, even communication becomes impossible across certain distances. Information travels at the speed of light, no faster. That's not just a technological limitation, it's a fundamental law of physics. If space expands fast enough between 2 points, light emitted from one point will never reach the other. The expansion carries it away faster than it can traverse the growing distance. So not only can we never reach those distant galaxies, we can never even send them a message, never receive one from them. Whatever civilizations might exist out there, whatever insights they might have into the nature of dark energy or anything else, we're cut off permanently. The universe, already so vast and empty that most of it is incomprehensibly remote, becomes even more isolated, even more fragmented. Islands of matter separated by oceans of expanding void, forever unable to interact. Now imagine you're a conscious being trillions of years in the future. Your ancestors somehow managed to survive the death of stars, maybe by building megastructures around black holes, harvesting their rotation energy through the Penrose process. Or maybe they've uploaded themselves into some substrate that doesn't require stars or planets. Digital consciousness running on quantum computers powered by black hole evaporation. You look out at the universe and see nothing. The cosmic microwave background has cooled to the point of undetectability. Every galaxy except those in your local cluster has disappeared beyond the cosmic horizon. Even your local cluster has merged into a single, enormous, elliptical galaxy, its stars long dead, its planets frozen airless husks. What do you think about existence, about meaning, about purpose? Do you even have the capacity to ask those questions anymore? Or has the slow grinding of entropy worn away the complexity necessary for philosophical inquiry? We don't know, can't know, but it's worth contemplating because it highlights something crucial about our current moment in cosmic history. We exist during an extraordinary epoch, the stelliferous era, astronomers call it, the age of stars. It will last from the first stars that formed a few 100 million years after the Big Bang to the last red dwarf that finally exhausts its fuel, maybe 100 trillion years total. We're only 14 billion years into that timeline, relatively early. The universe is still young, still energetic, still full of light and structure and complexity. Billions of years from now, after our sun has swelled into a red giant and engulfed the inner planets, after the Milky Way has collided with Andromeda and settled into a new equilibrium, after countless generations of civilizations have risen and fallen across the galaxy, the universe will still be expanding, still accelerating, and eventually the timeline extends beyond the stelliferous era into the degenerate era, when white dwarfs and neutron stars and black holes are all that remain. Then the black hole era, when even those exotic objects dominate the mass budget of the universe. And finally, the dark era, when the last black holes have evaporated and nothing remains but isolated photons and leptons spread so thin across such vast distances that interactions between them become vanishingly rare. Dark energy drives us toward that ending, relentlessly, indifferently, unless something changes. And here's a thought that keeps some physicists up at night. What if dark energy isn't eternal? What if it's a temporary phase, like inflation was in the earliest moments of the Big Bang? Inflation, you see, was a period of exponential expansion driven by a field called the inflaton. For a tiny fraction of a second, the universe doubled in size roughly every 10 to the power of 37 seconds. Space expanded faster than the speed of light, much faster. And then suddenly inflation ended. The inflaton field decayed, dumping its energy into matter and radiation, and the universe transitioned to the much slower expansion we see today. What if dark energy does the same thing? What if, at some point in the future, the vacuum energy that drives acceleration suddenly decays into some other form? The transition could be violent, universe-ending possibly, or it could settle into a new phase with completely different physics. We have no evidence this will happen, no theoretical reason to expect it, but we also have no evidence it won't happen. Dark energy could be metastable, sitting in what physicists call a false vacuum, and at any moment, quantum tunneling could trigger a transition to the true vacuum state. If that happens, a bubble of new vacuum would nucleate somewhere in the universe and expand at the speed of light, converting everything it touches to a new state with different physical laws, different values for fundamental constants, maybe no atoms, maybe no chemistry, maybe no possibility of complexity or life or consciousness, and we'd never see it coming. The bubble wall would arrive, moving at light speed, so there'd be no warning, no time to prepare. One instant, business as usual, the next instant, oblivion, sweet dreams. But let's assume dark energy remains constant. Let's trace out what that means for the evolution of cosmic structure in the deep future. Galaxies in our local group will eventually merge, as I mentioned. The Milky Way and Andromeda are already on a collision course, scheduled to interact in about 4 billion years. Other nearby galaxies will join the party. Eventually, you end up with a single, massive, elliptical galaxy, often called Milkomeda, in popular science articles, though that name makes me cringe every time I hear it. Within Milkomeda, though, things might remain relatively stable for an extremely long time. Gravity holds it together against the expansion of space. Stars will continue to orbit, their motions governed by the collective gravitational pull of all the other stars, the central supermassive black hole, whatever dark matter exists within the system. But stellar evolution continues. High-mass stars burn through their fuel quickly, exploding as supernova or collapsing into black holes. Medium stars like our Sun swell into red giants, shed their outer layers, and fade as white dwarfs. Low-mass red dwarfs burn slowly, frugally, potentially for tens or even hundreds of trillion of years, and with each generation, the available hydrogen gets used up. Star formation requires gas clouds, cold molecular hydrogen that can gravitationally collapse, but supernovae and stellar winds and radiation pressure from hot young stars can heat and disperse that gas, making it harder for new stars to form. Eventually, star formation ceases. The last generation of stars ignites. The cosmic countdown begins. Red dwarfs dominate this final stellar population. They're small, dim, cool, but incredibly long-lived. The smallest red dwarfs, those with only about 8% the mass of the Sun, could shine for 10 trillion years or more. 10 trillion years. Think about that time scale. The universe is currently 14 billion years old. 10 trillion years is roughly 700 times longer than the current age of the universe. Homo sapiens has existed for maybe 300,000 years. Recorded history covers about 5,000 years. 10 trillion years is a span of time so vast that all of human civilization, from the first cave paintings to whatever we become in the distant future, is less than a rounding error, a cosmic eye blink. And at the end of those 10 trillion years, the last red dwarf flickers and fades. The last ember of stellar fusion goes dark. The universe goes black. But it's not quite over. Stellar remnants remain. White dwarfs slowly cooling. Neutron stars spinning down as they radiate energy. Black holes, patient and eternal, or so it seems. White dwarfs crystallize as they cool. Carbon and oxygen atoms arrange themselves into lattice structures. The star becomes a diamond the size of Earth, floating through the void, radiating away its residual heat on timescales measured in quadrillions of years. Eventually, even white dwarfs reach thermodynamic equilibrium with the cosmic microwave background. They stop cooling because there's nothing colder to radiate heat to. They just exist, inert, dark, cold, unless proton decay happens. This is speculative, remember. We've never observed a proton decay. The experimental lower limit on proton half-life is something like 34 years. But many grand unified theories predict that protons should eventually decay, transforming into lighter particles through processes that violate baryon number conservation. If protons decay, then over timescales of 10 to 40 years or so, even the white dwarfs disintegrate. The atomic nuclei that make them up simply fall apart, converting into radiation and lighter particles. The same thing happens to neutron stars, though the details are more complicated because of the extreme densities involved. What's left? Electrons, positrons, neutrinos, photons, and black holes. Black holes seem eternal. Nothing escapes them, or so classical physics says. But quantum mechanics tells a different story. Stephen Hawking showed in the 1970s that black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon. Virtual particle pairs pop into existence near the boundary, and occasionally one particle escapes while the other falls in. The net effect is that the black hole radiates energy and slowly loses mass. This Hawking radiation is astonishingly weak for large black holes. The temperature of the radiation is inversely proportional to the mass. A solar mass black hole has a temperature about 10 million times colder than the cosmic microwave background. It absorbs more radiation from the surrounding universe than it emits. It grows very slowly rather than shrinking, but as the universe expands and cools, the cosmic microwave background temperature drops. Eventually, it becomes colder than the Hawking radiation from even small black holes, At that point, black holes start to evaporate. The time it takes is staggering. A solar mass black hole would require about 10^67 years to evaporate completely. A supermassive black hole like the one at the center of our galaxy, with 4 million times the Sun's mass, would take roughly 10 to 100 years, 10 to the power of 100 years. There's no adequate way to conceptualize such a number. It's not just large, it's incomprehensibly beyond large. The number of atoms in the observable universe is around 1080. The number of possible quantum states in the observable universe is maybe 10 or 120. We're talking about timescales that dwarf even these cosmic quantities. During all this time, space continues to expand. Galaxies, if you could even call them that anymore, the remnant collections of stellar corpses and black holes drift farther and farther apart. The distance between any two objects grows without limit. Individual particles become separated by distances so vast that they're causally disconnected. A photon emitted from one particle will never, even given infinite time, reach another particle because the expansion of space carries them apart faster than light can traverse the growing distance. The universe becomes a collection of isolated systems, each fundamentally unable to interact with any other. No information exchange, no causality, no connection. Each black hole, as it evaporates, releases its mass energy back into the universe as Hawking radiation. Mostly photons with a small admixture of other particles. These particles scatter into the void, their wavelength stretching as space expands, their energy redshifting toward zero. When the last black hole evaporates, the universe contains only radiation and a few scattered leptons. The temperature approaches absolute zero asymptotically. Entropy approaches a maximum. Energy becomes uniformly distributed across infinite space. Heat death. The final equilibrium. A state of maximum disorder from which no further evolution is possible. Nothing happens anymore. Nothing can happen. There's no gradient, no difference in energy or temperature or density to drive change. The universe reaches a state of perfect, eternal stasis. Or does it? Because quantum mechanics is weird. Deeply, profoundly weird. And one of the weird predictions of quantum field theory is that vacuum fluctuations can, given enough time, produce anything, including, theoretically, entire new universes. The timescales involved make black hole evaporation look instantaneous. We're talking 1050 years or something similarly absurd for a quantum fluctuation to produce a new Big Bang scale event. But in an infinite future, even probabilities that small become certainties, given enough time, anything that can happen will happen. So maybe the universe doesn't really end. Maybe it just cycles through periods of activity and dormancy, with new Big Bangs spontaneously nucleating from quantum fluctuations in the vacuum, creating pocket universes that expand and evolve and eventually decay back into empty space over and over forever. Or maybe not. Maybe the heat death is genuinely final. Maybe there's a hard limit to what quantum fluctuations can produce, and truly large-scale structures simply cannot emerge from the void. We don't know. Do you see the pattern here? Every answer leads to we don't know. Every investigation terminates in uncertainty. Why is the universe expanding? We don't know. What is dark energy? We don't know. Will expansion continue forever? Probably, but we don't know for certain. What happens after heat death? We don't know. Is there anything beyond our cosmic horizon? We don't know. Are there other universes? We don't know. Is our understanding of physics complete, or are there Deeper layers we haven't discovered. We don't know. It's humbling, frustrating, exhilarating. Because we don't know isn't a stopping point. It's an invitation, a challenge, a reason to keep looking, keep measuring, keep thinking. And we are making progress, even if it doesn't always feel like it. Consider what we've learned just in the past few decades. We've measured the cosmic microwave background to incredible precision, mapping temperature fluctuations that reveal the structure of the universe when it was only 380,000 years old. We've used those measurements to determine the geometry of space itself. It's flat, by the way, or so close to flat that we can't measure any curvature. We've detected gravitational waves, ripples in space-time itself, confirming a major prediction of general relativity and opening an entirely new window onto the universe. We can now observe phenomena that emit no light, colliding black holes, merging neutron stars, possibly even the Big Bang itself. And through primordial gravitational waves, we photographed the event horizon of a supermassive black hole using an array of telescopes scattered across the Earth to create a planet-sized virtual telescope. The image looks exactly like the simulations predicted, a glowing ring of light surrounding a dark circle. General relativity, once again, proven correct in an extreme regime. We've discovered thousands of exoplanets, planets orbiting other stars, and we're beginning to characterize their atmospheres. We're searching for biosignatures, chemical evidence of life on worlds light years away. We might find it. We might discover we're not alone. We've built detectors to search for dark matter directly, burying them deep underground to shield them from cosmic rays, cooling them to millikelvin temperatures, waiting for the incredibly rare collision between a dark matter particle and an atomic nucleus. So far, nothing. But we keep refining the technology, closing the parameter space, narrowing down what dark matter could be. We're planning missions to send probes to other star systems. Breakthrough Starshot aims to accelerate tiny spacecraft to 20% the speed of light using powerful lasers, sending them to Alpha Centauri on a 20-year journey. It's ambitious, maybe impossible, but we're trying. All of this while living on a rock that's 93 million miles from a medium-sized star in the suburbs of a typical galaxy in an unremarkable region of space. The fact that we can know anything about cosmic expansion, about dark energy, about the fate of the universe is extraordinary. We have no business being able to figure this stuff out. Our brains are 3-pound meat computers optimized for survival, not cosmology. And yet, here's what really gets me. The universe doesn't care if we understand it. It's not trying to teach us anything. It's not presenting mysteries for our edification. It simply is, operating according to physical laws that exist, whether or not anyone comprehends them. For billions of years before humans evolved, the universe expanded. Dark energy pushed galaxies apart. Stars formed and died. Black holes merged. And none of it meant anything to anyone because there was no one to observe it, to measure it, to wonder about it. Then, on one small planet, organic chemistry became complex enough to replicate. Darwinian evolution produced increasingly sophisticated organisms. Eventually, neurons, brains, consciousness, self-awareness, and suddenly the universe had observers, tiny, temporary, fragile, but capable of looking outward and asking, what is all this? Where did it come from? Where is it going? We're the universe's way of knowing itself. That sounds like a cliche, I know. Carl Sagan said it better than I ever could. But it's true and it's profound. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in the cores of stars that exploded billions of years ago. You are made of star stuff, not metaphorically, literally. And now that star stuff has arranged itself into a configuration capable of pondering its own origin, of measuring cosmic expansion, of discovering dark energy, that's either a meaningless accident or the most significant thing that's ever happened in the history of the universe. I tend toward the latter interpretation, but I acknowledge the former is entirely possible, because meaning isn't something the universe provides. It's something we create, we impose. We decide what matters, what's important, what's worth pursuing. The universe expanding into heat death doesn't have to be depressing. It could be liberating. Nothing we do matters on cosmic scales. Great. Then we're free to define our own meaning, our own purpose, without worrying about some ultimate cosmic scorecard. We're here. We're conscious. We can think and feel and love and create. We can build telescopes and write equations and make art and tell stories. We can look up at the night sky and recognize that those points of light are actually distant suns, many of them surrounded by their own planets, and that the light we're seeing was emitted years or centuries or millennia ago, and that we're seeing into the past every time we look up. We can understand that the universe is expanding, that it's been expanding for nearly 14 billion years, that it's accelerating, that dark energy is driving it toward a cold, dark, distant future. And we can choose to find that beautiful, terrifying and beautiful, because we're part of it. We're not separate from the universe. Looking in from outside, we're embedded in it. We're made of it. When we observe cosmic expansion, we're literally the universe observing its own expansion. Every measurement we make, every theory we develop, every piece of knowledge we gain is the universe coming to understand itself. And maybe that's enough. Maybe that's all the meaning we need. The universe is expanding. We don't fully understand why. We might never fully understand why. Dark energy remains mysterious, possibly forever beyond our complete comprehension. But we keep trying. We keep building bigger telescopes, more sensitive detectors, more powerful computers to run more sophisticated simulations. We keep thinking, questioning, exploring, not because we'll necessarily succeed, not because there's some cosmic reward for understanding, but because it's what we do, it's who we are. We're the species that looks at the stars and asks questions, and as long as we're around, as long as consciousness persists anywhere in this vast, expanding cosmos, those questions will continue. The universe doesn't owe us answers, but we're going to keep asking anyway. And that defiance, that stubborn refusal to accept ignorance might be the most human thing about us. Think about what we're really doing here. We're creatures who live maybe 80 years if we're lucky. We exist on a planet that's 4.5 billion years old in a universe that's 13.8 billion years old, contemplating timescales of trillions upon trillions of years. We're mayflies trying to understand eternity. It should be absurd, it should be impossible, but we're doing it anyway. There's something almost defiant about the entire scientific enterprise when you think about it. The universe presents us with mysteries wrapped in enigmas, phenomena so far beyond human scales that we shouldn't be able to even conceive of them, let alone measure them. And we respond by building instruments, developing mathematics, constructing theories. We take the universe's challenge and we meet it head on. Dark energy is just the latest in a long line of cosmic puzzles that seemed unsolvable until they weren't. Every generation of scientists faces phenomena that appear inexplicable, that challenge the existing paradigms, that force us to expand our understanding. A century ago, we didn't know galaxies existed. We thought the Milky Way was... the entire universe. Then Edwin Hubble, using the largest telescope available at the time, resolved individual stars in what we thought were nebulae and proved they were actually separate galaxies, island universes unto themselves, scattered through space like cities of light in an ocean of darkness. The universe got bigger, vastly bigger. Then came the realization that it was expanding. That universe got dynamic, temporal, historical. It had a past and a future, not just an eternal present. Then the cosmic microwave background, evidence of a hot, dense beginning. The Big Bang, confirmed. Then dark matter, this invisible scaffolding that outweighs visible matter 5-to-1, holding galaxies together with its gravity, even though we can't see it, can't touch it, can barely detect it. And now dark energy, stranger still, comprising 68% of everything, pushing the universe apart with increasing force. Each discovery makes the universe stranger, more alien, less intuitive, further from our everyday experience, but also more knowable, more mapped, more understood, even when that understanding is mostly we don't know yet, because there's a difference between we don't know and we can't know. The former is temporary, a challenge, the latter is a surrender, and science doesn't surrender easily. Take dark matter. We don't know what it is yet. Decades of searching haven't produced a definitive detection. Underground detectors sitting in silence, waiting for a dark matter particle to collide with an atomic nucleus. Nothing. Particle accelerators smashing protons together at nearly the speed of light, looking for dark matter particles in the debris. Nothing. Telescopes scanning the sky for gamma rays that might signal dark matter annihilation. Nothing. But we're not giving up. We're building more sensitive detectors, exploring different theoretical candidates, primordial black holes, axions, sterile neutrinos, modified gravity. Each possibility carefully examined, tested, constrained. Eventually we'll figure it out, or we'll eliminate enough possibilities that the answer becomes obvious by process of elimination. Dark energy will be the same. Right now, it's a mystery, but mysteries have a way of yielding to sustained investigation. The universe keeps its secrets, but not forever, not from a species determined enough to keep asking questions. And here's what gives me hope. We've been wrong before, spectacularly wrong. And every time we've been wrong, the truth turned out to be more interesting than what we'd imagined. Newton's gravity was wrong, not entirely wrong, but incomplete. It worked beautifully for centuries, accurately predicting planetary orbits, explaining tides, allowing us to send spacecraft to other planets. And Einstein came along and showed that gravity isn't a force at all. It's curved space-time. Mass and energy warp the fabric of space and time, and objects follow the straightest possible paths through that curved geometry. General relativity was so counterintuitive, so mathematically complex, so far beyond common sense that even many physicists initially rejected it. But it made predictions. The perihelion precession of Mercury, which Newtonian gravity couldn't fully explain. The bending of starlight during a solar eclipse confirmed by Arthur Eddington in 1919. Gravitational time dilation, now measured so precisely that GPS satellites have to account for it, or they'd give you the wrong directions. Reality was stranger than anyone had imagined, and more beautiful. Quantum mechanics was the same way. The idea that particles could be in multiple states simultaneously until observed, That measurement fundamentally changes what's being measured, that uncertainty is built into the fabric of reality at the smallest scales. It seemed absurd. Einstein himself rejected parts of it, famously declaring that God doesn't play dice with the universe. But the experiments kept confirming quantum predictions. The double-slit experiment showing wave-particle duality, quantum entanglement, spooky action at a distance, the Heisenberg uncertainty principle, all of it verified to extraordinary precision. Reality, once again, stranger than fiction. So when we encounter dark energy and find ourselves baffled when our best theories produce predictions that are wrong by 120 orders of magnitude, when we can measure its effects but not explain its origin, maybe we're just at the beginning of another paradigm shift. Maybe dark energy will lead us to a deeper understanding of space-time itself. Maybe it'll require revisions to general relativity that reveal new aspects of gravity we've never suspected. Maybe it'll connect to quantum mechanics in ways we haven't imagined, finally providing a clue toward quantum gravity, the holy grail of theoretical physics. Or maybe it's something completely different. It's something so far outside our current conceptual framework that we can't even formulate the right questions yet. The history of science suggests that the truth will be stranger and more wonderful than any of our current speculations. But here's the thing, we have to be around to find out. And that's not guaranteed. The universe is expanding, yes. Dark energy is pushing galaxies apart, yes. But long before any of that becomes a practical concern for humanity, we have more immediate problems: climate change, nuclear weapons, artificial intelligence, engineered pandemics, asteroid impacts, any number of existential risks that could end human civilization or even extinguish our species entirely. We could discover the nature of dark energy, solve the mysteries of cosmic expansion, develop a complete theory of quantum gravity, and still destroy ourselves through short-sightedness or negligence or malice. The universe doesn't care. It'll keep expanding whether we're here to observe it or not. But we should care, because consciousness, intelligence, the ability to understand and appreciate the universe, these things might be rare, precious, worth preserving. We don't know if life exists elsewhere. We don't know if intelligence has arisen on other worlds. The galaxy could be teeming with civilizations, or we could be utterly alone. The Fermi paradox, the question of where all the aliens are, remains unanswered. Maybe intelligence is common and we just haven't been looking long enough or in the right ways. Maybe there are millions of civilizations scattered across the galaxy, each discovering dark energy independently, each grappling with the same cosmic mysteries. Or maybe intelligence is vanishingly rare. Maybe the chain of events required to produce technological civilization is so unlikely that it's only happened once in the observable universe. Maybe we're it. The only minds capable of understanding cosmic expansion, the only observers who can appreciate the universe's strange beauty. If that's true, then our destruction would be a cosmic tragedy. Not because the universe would miss us, but because something genuinely unique and valuable would be lost. Imagine the universe finally producing observers after billions of years of blind evolution, only to have those observers destroy themselves before they fully understand what they're part of, before they spread beyond their home planet, before they make contact with others. If others exist, it would be like building a telescope of unprecedented power and then smashing it before taking the first photograph. So maybe the real question isn't just, is the universe expanding, but will we survive long enough to fully understand the answer? Because understanding takes time. It takes sustained effort across generations. It requires stability, resources, cooperation on global scales. It requires choosing to invest in knowledge rather than destruction, in exploration rather than exploitation. We've made that choice before. The Apollo program put humans on the moon. The Hubble Space Telescope revealed the deep universe in unprecedented detail. The Large Hadron Collider discovered the Higgs boson. The Event Horizon Telescope photographed a black hole. These weren't easy projects. They required billions of dollars, decades of work, thousands of people coordinating across national boundaries. They happened because we collectively decided they were worth doing. We can make that choice again. We can choose to keep exploring, keep investigating, keep pushing the boundaries of knowledge, not because it's profitable in the short term, not because it provides immediate practical benefits, but because understanding the universe is one of the most worthwhile things conscious beings can do. And who knows, maybe understanding dark energy will have practical applications we can't currently foresee. Maybe it'll lead to new technologies, new ways of manipulating space-time, new possibilities for civilization. Or maybe it won't. Maybe it'll remain purely abstract. Knowledge, interesting only to cosmologists and philosophers. But even if that's the case, even if dark energy never leads to practical technology, the knowledge itself has value, because we're not just survival machines, we're not just gene replication devices trying to maximize our inclusive fitness. We're conscious beings capable of appreciating beauty, understanding complexity, finding meaning in the patterns of existence. The universe is expanding. That's a fact about reality, independent of whether it makes us happy or sad, whether it aligns with our preferences or defies them. But how we respond to that fact, that's up to us. We can see it as depressing, a march toward inevitable heat death and cosmic isolation, or we can see it as context, a reminder of our place in space and time, a framework for understanding our existence. We live in a brief window of cosmic history when stars still shine, when galaxies are visible, when the cosmic microwave background hasn't been stretched into undetectability, when intelligent life, at least on Earth, has arisen and is capable of asking questions about its origins and fate. Billions of years from now, observers in our galaxy, if any exist, won't have the evidence we have. They'll be missing crucial pieces of the puzzle. Billions of years ago, observers, if any existed, wouldn't have had the evidence either. Stars were different, galaxies were arranged differently. The universe was denser, hotter, younger. We exist at this particular moment. We have access to this particular set of evidence. We can see things that past observers couldn't and future observers won't. That's either random chance or profound luck, depending on your perspective. Either way, it seems worth taking advantage of, worth using our limited time and resources to learn as much as we can while the learning is still possible. Because the universe won't wait for us. It's expanding right now as you read this. Galaxies are receding. Space is stretching. Dark energy is pushing everything apart with increasing force. Every second that passes, some distant galaxy crosses our cosmic event horizon and disappears from view forever. Some bit of information becomes permanently inaccessible. Some question becomes forever unanswerable. The window is closing, slowly, imperceptibly, but inexorably. So we build our telescopes, we launch our spacecraft, we develop our theories, we train new generations of scientists to continue the work when we're gone. We do this knowing we might not find all the answers, knowing that some mysteries might remain unsolved despite our best efforts, knowing that the universe might keep its deepest secrets forever. But we try anyway, because what's the alternative? Giving up, accepting ignorance, resigning ourselves to never knowing what dark energy is, where it comes from, why it exists. That's not who we are. That's not what humans do. We're the species that looked at the sky and decided to go there. That invented mathematics to describe nature. That split the atom and decoded DNA and photographed Earth from the moon. We're the species that asks why. And sometimes the asking is as important as the answer. The universe is expanding. We know that now. We've measured it. We've quantified it. We've traced its history back to the Big Bang and projected its future forward to heat death. But we don't fully understand it yet. Dark energy remains mysterious. The ultimate fate of the universe remains uncertain. Deeper questions about the nature of space, time, matter, and energy remain unanswered. Those questions are our inheritance, our challenge, our opportunity. Every generation builds on what came before. Newton stood on the shoulders of giants, and Einstein stood on Newton's shoulders, and future scientists will stand on Einstein's shoulders, seeing farther and deeper than any of their predecessors. Eventually, maybe centuries from now, maybe millennia, someone will understand dark energy. They'll develop a theory that explains it completely, that makes testable predictions, that reveals its place in the cosmic order. And when that happens, when the mystery finally yields to human ingenuity and persistence, it'll be one of the great triumphs of the scientific enterprise. But it'll also open new questions, deeper mysteries, further horizons, because that's how knowledge works. Each answer spawns new questions. Each solved mystery reveals deeper mysteries underneath. The onion is infinite. And we keep peeling, not because we'll ever reach the center, not because there's some final truth waiting at the end of the investigation, but because the peeling itself, the investigation, the exploration, the sustained effort to understand, that's what makes us human. That's what gives meaning to our brief flicker of consciousness in an incomprehensibly vast and ancient universe. The universe is expanding. It doesn't know we exist. It doesn't care that we're trying to understand it. It simply is operating according to laws that exist with or without observers. But we exist. We care. We're trying. And in a universe that's mostly empty space, mostly dark matter and dark energy, mostly things we can't see or touch or directly detect, that caring might be the most remarkable thing of all. We're here, we're conscious, we're asking questions about cosmic expansion and dark energy and the ultimate fate of everything. We might be the only ones doing so in the entire observable universe. Or we might be one of countless civilizations scattered across the cosmos, each asking the same questions, each grappling with the same mysteries. We don't know, but we're going to keep looking, keep measuring, keep thinking, because that's what we do. That's who we are. We're the universe's way of understanding itself. And the universe is still expanding, still accelerating, still racing toward some distant future we can barely glimpse. But we're here to witness it, to measure it, to wonder about it, and maybe, just maybe, to understand it. Not today, not tomorrow, not in our lifetimes probably, but eventually. Because we don't give up easily, we never have. The universe threw dark matter at us and we didn't give up. We built detectors, we refined theories, we kept searching. The universe threw cosmic expansion at us and we didn't give up. We measured redshifts. We observed supernovae. We mapped the cosmic microwave background. The universe threw dark energy at us, and we're not giving up now. We're building better telescopes, developing more sophisticated models, exploring every possibility. And one day, someone will figure it out. They'll crack the code, solve the mystery, understand what dark energy actually is. And when they do, they'll be standing on the shoulders of everyone who came before, everyone who measured a redshift, everyone who observed a supernova, everyone who wondered why the universe is expanding and had the courage to seek an answer. That's how progress happens. Incrementally, generationally, each researcher adding a small piece to an enormous puzzle that might never be completed, but is always worth working on. The universe is expanding. We don't fully know why, but we're working on it. And we won't stop until we understand, or until the universe itself prevents us from continuing, whichever comes first. Because in the end, that's all we can do. All any conscious beings can do, exist. Observe, question, explore. Make meaning in a universe that provides none. Find beauty in the mathematics of expansion. See wonder in the mystery of dark energy. And refuse to accept ignorance as final. The universe doesn't owe us understanding, but we're going to pursue it anyway. For as long as we exist, for as long as stars shine, for as long as consciousness persists anywhere in this vast, expanding, accelerating cosmos, we're here, we're watching, we're wondering, and the universe, indifferent and magnificent, continues its eternal expansion into the darkness beyond, taking us with it, whether we understand why or not. But here's what haunts me late at night, when I'm alone with my thoughts and the weight of cosmic insignificance presses down. What if we're looking at this all wrong? What if dark energy isn't the anomaly? What if we are? Stay with me. We live in a universe where the fundamental forces are precisely calibrated to allow for complexity. The strong nuclear force binds protons and neutrons into atomic nuclei. If it were slightly weaker, only hydrogen would exist. Slightly stronger, and hydrogen would be too unstable to form. Either way, no chemistry, no complex molecules, no life. The electromagnetic force governs how atoms bond into molecules. If it were different by even a small percentage, water wouldn't have the properties it does. Carbon wouldn't form long chains. The chemistry of life as we know it would be impossible. Gravity is absurdly weak compared to the other forces. A tiny magnet can overcome the gravitational pull of the entire Earth, but if gravity were stronger, stars would burn too hot and fast for life to evolve on planets orbiting them. Weaker, and stars might never ignite at all. The cosmological constant, the vacuum energy that might be dark energy, sits at a value that's small enough to allow galaxies to form, but large enough to eventually dominate the universe's expansion. If it were much larger, the universe would have expanded so rapidly that matter could never clump together. No galaxies, no stars, no planets, no us. These aren't approximations. These are razor-thin margins. The universe appears to be fine-tuned for our existence, which leads to one of the most troubling questions in all of physics. Why? 3 possibilities present themselves, and none of them are particularly satisfying. First, coincidence. We happen to live in a universe where the constants have the values they do, and if they didn't, we wouldn't be here to notice. This is the anthropic principle, and it's simultaneously obvious and deeply unsatisfying. Yes, we can only observe universes capable of producing observers, but that doesn't explain why this universe has the properties it does. It's like shuffling a deck of cards and dealing yourself a royal flush, then saying, well, I could only be looking at these cards if they were a royal flush. technically true but missing the point entirely. Second, design. Some entity or intelligence deliberately configured the universe to allow for life. This pushes the question back one level without answering it. Who designed the designer? And it's not a scientific hypothesis because it makes no testable predictions. Third, the multiverse. There are countless universes, each with different values for the fundamental constants, and we happen to live in one of the rare ones where the constants allow for complexity and life. This is more scientifically respectable because some versions of it make testable predictions, but it also feels like a cop-out. We can't explain why our universe has the properties it does, so we postulate infinite other universes we can never observe or interact with. But if the multiverse is real, if there are countless universes with different physical laws, then dark energy might be perfectly normal. Our universe might be utterly typical. And the real mystery isn't why dark energy exists, but why the other forces and constants are configured to allow for stars and planets and life. Maybe we're the anomaly. Maybe universes dominated by dark energy expanding rapidly into cold emptiness are the default. And we just happen to exist during the brief window when matter can clump together and form interesting structures before dark energy takes over completely. There's a term for this, the stelliferous era, the age of stars. It spans from the first stars, forming a few 100 million years after the Big Bang, to the last stars, red dwarfs that will burn for tens of trillions of years. In the grand timeline of the universe, the stelliferous era is brief, a few trillion years out of an infinite future, a tiny fraction of cosmic history. Before it, the Dark Ages. After it, the degenerate era, the black hole era, the dark era. Epochs where stars don't exist, where the universe is dark and cold and empty. We exist during one of the only periods when the universe is interesting, when there's light, when complex chemistry can occur, when life is possible. Is that coincidence? Anthropic principle? Design? Multiverse selection? We don't know, but it suggests something profound. The universe we see, the one filled with galaxies and stars and planets, might not be the universe's natural state. It might be a temporary aberration, a brief spark of complexity in an otherwise simple, empty, eternal expansion. Dark energy might be the universe reverting to its default condition, and everything we consider normal matter and structure and light might be the actual anomaly. That reframes the question entirely. Instead of asking, why does dark energy exist? We should be asking, why does anything else exist? Why is there matter instead of just empty space? Why did the Big Bang produce particles and antiparticles in slightly unequal amounts, leaving a small excess of matter when they annihilated? Why did that matter clump together under gravity instead of remaining uniformly distributed? These aren't new questions. Physicists have been wrestling with them for decades, but viewing them through the lens of dark energy dominance adds a new perspective. Maybe the universe wants to be empty. Maybe the natural tendency is toward maximum entropy, uniform expansion, eventual heat death. And the brief period where structure exists, where entropy can decrease locally by increasing globally, where life can emerge and ask questions about its own existence. Maybe that's the miracle, the improbable deviation from the norm. We spend so much time wondering about dark energy, this mysterious force pushing the universe apart. But maybe we should spend more time marveling that anything resisted that push long enough to create stars, to create us, because gravity is fighting a losing battle. Always has been. Even before we discovered dark energy, even when we thought expansion was slowing down, gravity was never going to win. The universe was never going to recollapse. The matter density was too low, the expansion too fast. And now with dark energy accelerating the expansion, gravity doesn't stand a chance. It can hold together local structures, galaxies and galaxy clusters, but on larger scales, space itself is winning. The universe is becoming increasingly empty, increasingly isolated, increasingly simple. This is where cosmology gets philosophical. Because if the universe is destined for heat death, if all structure will eventually dissolve, if consciousness is doomed to extinguish when the last stars fade, then what was the point? Did the universe need a point? Does existence require justification? These aren't scientific questions. Science can tell us what the universe is doing, how it's evolving, what its ultimate fate will likely be. But science can't tell us whether that matters, whether it means anything, whether we should care. That's on us. That's the domain of philosophy, of meaning-making, of individual choice. Some people find the heat death of the universe depressing, nihilistic, evidence that nothing matters because everything ends. I think that's backwards. If the universe were eternal and unchanging, if galaxies hung in space forever, if stars never died, if nothing ever ended, then individual moments wouldn't matter. Any given instant would be identical to every other instant. There'd be no uniqueness, no scarcity, no reason to value anything because there'd always be more of it. But the universe isn't eternal. Stars have lifespans. Galaxies will eventually go dark. Consciousness exists for a finite time in a finite region of space, and that finitude creates value, creates meaning, makes moments matter precisely because they don't last forever. You and I having this conversation, contemplating the expansion of the universe and the mystery of dark energy, this moment is unique. It's never happened before. It'll never happen again. In a few decades, we'll both be dead. In a few billion years, Earth will be consumed by the sun. In trillions of years, the Milky Way will be dark. In incomprehensibly vast stretches of time, even black holes will evaporate. But right now, in this moment, we exist, we're conscious, we can think about these things. That's not depressing, that's extraordinary. The universe doesn't guarantee meaning, it doesn't provide purpose, it doesn't care about our hopes or fears or dreams, but it allows for meaning, provides the substrate for purpose, creates the conditions where conscious beings can exist, at least temporarily, and decide for themselves. What matters? Dark energy will eventually win. The universe will expand into cold, dark, empty space. All structure will dissolve. All complexity will fade. Entropy will reach its maximum. But not yet, not today, not for trillions of years. We have time. Not infinite time, but time nonetheless. Time to explore, to discover, to understand, to create, to love, to make meaning in a universe that provides none. And maybe that's enough. Maybe that has to be enough, because the alternative is to give up. To say that because the universe will eventually end in heat death, nothing we do matters, that because dark energy will eventually isolate every galaxy beyond every other galaxy's cosmic horizon, there's no point in trying to understand it. But that's not how humans work. That's not how consciousness works. So we don't need cosmic significance to find meaning. We don't need the universe to care about us, to care about each other, about our work, about our understanding. We create meaning. We impose it on an indifferent cosmos. And that self-generated meaning is just as real, just as valid as any meaning the universe might have provided, maybe more so, because it's ours. We made it. We chose it. The universe is expanding. We didn't choose that. We can't change it. Dark energy exists whether we like it or not, but how we respond, what we do with the time we have, what we choose to value and pursue and protect, that's entirely up to us. And I choose to find beauty in cosmic expansion, wonder in dark energy, meaning in the sustained human effort to understand what we're part of, not because the universe rewards that choice, not because it'll prevent heat death or make consciousness eternal, but because the alternative, accepting ignorance and giving up on understanding, feels like a betrayal of what makes us human. We're the species that asks why. That's our defining characteristic, our superpower, our curse, and our glory. And as long as we exist, as long as consciousness persists anywhere in this expanding universe, that questioning will continue. We'll build telescopes that can see to the edge of the observable universe. We'll develop theories that explain dark energy. We'll map the cosmic web in exquisite detail. We'll search for life on other worlds. We'll send probes to other star systems, not because any of it will stop the expansion, not because it'll prevent our eventual extinction, but because we can, because we're here, because the universe, for a brief moment in cosmic time, has produced beings capable of understanding it, and that capability feels too precious to waste. So we use it, we push it to its limits, we see how far we can go, how much we can learn, how deeply we can understand, and when we're gone, when humanity has run its course, when the sun has died and Earth is nothing but a frozen cinder orbiting a white dwarf, the universe will continue, expanding, accelerating, indifferent, but for a little while, for this cosmically brief moment, we were here, we existed. We looked out at the expanding universe and we understood, at least partially, what we were seeing. We measured the redshift of distant galaxies. We discovered dark energy. We contemplated our place in the cosmic order. We were the universe's way of knowing itself, and that counted for something. Not to the universe. The universe doesn't keep score, doesn't care, doesn't remember, but to us, to our children, to the long chain of humans who came before us and wondered about the stars, and the long chain who will come after us and continue the work. To them it matters, to us it matters, and maybe that's all the mattering that exists. All the meaning there is, local, temporary, self-generated, but real. The universe is expanding, dark energy is pushing it apart, heat death awaits in the incomprehensibly distant future, and we're here, right now, trying to understand it all. Tiny, temporary, fragile, but conscious, curious, determined, and in a universe that's mostly empty space, that's mostly things we can't see or understand, that's mostly indifferent to our existence. Now, that's not nothing, that's everything. There's a photograph that should disturb you more than it probably does. The Hubble Deep Field. You've likely seen it. A tiny patch of sky, seemingly empty, no bigger than a grain of sand held at arm's length. Hubble stared at it for 10 days straight in 1995, gathering every photon it could from that apparently blank region of space. And what emerged was staggering 3,000 galaxies in that tiny speck, each galaxy containing hundreds of billions of stars, each star potentially surrounded by planets. And this was just one random patch of sky among the millions of such patches we could observe. Do the math, extrapolate across the entire sky. The numbers become incomprehensible. 2 trillion galaxies in the observable universe. each one an island of hundreds of billions of stars. The total number of stars exceeds the number of grains of sand on all of Earth's beaches. And we're worried about dark energy, about cosmic expansion. Maybe we should be more worried about what all those galaxies contain, what we're missing, what we'll never know about, because the light will never reach us. Because here's the thing nobody wants to say out loud. We're not just losing galaxies to cosmic expansion. We're losing information, possibilities, potential. Every galaxy that crosses our cosmic event horizon doesn't just disappear from view. It takes with it every star system, every planet, every potential civilization that might have evolved there, every discovery they might have made, every insight they might have had into dark energy or quantum gravity or questions we haven't even thought to ask yet. Gone forever. Not destroyed, but forever. Inaccessible. Might as well not exist from our perspective. And this is happening right now, not in some distant future. Right this second, as you process these words, galaxies are crossing the threshold. Entire cosmic neighborhoods are being cut off from us by the expansion of space. We talk about dark energy abstractly as a physics problem to be solved. But it's more than that. It's a clock, a countdown, a closing window on the universe's knowability. And we're sitting here on Earth, barely able to get humans to the moon anymore, arguing about budgets and politics and short-term problems, while the cosmic library burns. Not literally burns. Worse, it's being carried beyond the speed of light, placed forever out of reach while we watch helplessly. That should bother us more than it does. Because what if the answer to dark energy isn't in our cosmic neighborhood? What if some galaxy that's currently observable but won't be in a billion years contains a natural phenomenon that would make dark energy obvious? A naked singularity, a bubble universe collision, some exotic structure that would make a physicist say, oh, of course, that's what dark energy is. And we'll miss it. We'll lose it. And future cosmologists will never even know what they don't know. This has happened before, by the way. We're not the first generation to lose evidence. The cosmic microwave background, that faint afterglow of the Big Bang, is already cooling. Right now, it has a temperature of about 2.7 Kelvin. In the far future, it'll cool to the point where it's indistinguishable from the background noise of empty space. Future observers won't be able to detect it. They'll lose the most direct evidence for the Big Bang itself. They'll look at the universe and see isolated galaxies in a sea of darkness. No expansion, because there won't be distant galaxies to measure redshift from. No cosmic microwave background to analyze. No large-scale structure showing the signature of early universe inflation. They'll build theories based on incomplete data. And they'll be wrong, not because they're bad scientists, but because the evidence they need will have literally moved beyond their reach. We're luckier we exist during a window when the evidence is still accessible, when we can still see the cosmic microwave background, when distant galaxies are still visible, when the universe's history is still written in the light reaching us from all directions. But that window is closing, not quickly on human timescales, but inexorably on cosmic ones, which raises an uncomfortable question. What evidence have we already lost? What happened in the early universe that left no detectable signature? What existed before inflation that was erased by inflation itself? We assume the Big Bang was the beginning, but what if it wasn't? What if there was something before, that some previous state or previous universe, and the Big Bang erased all evidence of it? We'd never know. The data would be gone, destroyed by the very event we're trying to study. It's like trying to understand an explosion by examining the crater afterward. You can learn some things. You can measure the size, analyze the debris, reconstruct the approximate energy, but you can't know exactly what exploded or why, or what existed in that space before the explosion occurred. The universe might be the same way. We're examining the aftermath, measuring the expansion, cataloging the debris. But the initial conditions, the trigger, the reason it all happened, that might be forever beyond our reach. Not because we're not smart enough, not because we lack the right instruments, but because the information was destroyed, erased, lost to entropy or inflation or whatever came before the Big Bang. And dark energy is doing the same thing to our future. It's erasing information and carrying away evidence, reducing the knowability of the universe, one receding galaxy at a time. Some physicists think information can't be destroyed. The holographic principle suggests that information about anything that falls into a black hole is preserved on the event horizon. Hawking radiation carries information back out. Nothing is truly lost, but that's for black holes. Local phenomena. What about cosmic expansion? What happens to information when galaxies cross the cosmic event horizon? Is it preserved somehow, encoded in some substrate we can't access? Or is it genuinely lost, deleted from our universe's reference frame, gone in a way that violates information conservation? We don't know. The physics of cosmic horizons isn't as well understood as the physics of black hole horizons. We're still working it out. But if information is being destroyed, if dark energy is genuinely erasing parts of the universe's history and structure from accessibility, then we're living through a cosmic tragedy. A slow-motion catastrophe where the universe forgets itself piece by piece. And we might be the only ones who notice, the only consciousness anywhere in our cosmic neighborhood that's aware of what's being lost. That carries a certain responsibility, doesn't it? If we're the universe's memory, at least for this region of space-time, then forgetting is a kind of death, not our death, the universe's death, the death of information and possibility and knowability. We can't stop it. Can't reverse cosmic expansion, can't switch off dark energy or prevent galaxies from receding, but we can observe, record, remember? We can catalogue every galaxy while we still can, map the cosmic web in exquisite detail, measure the properties of dark energy with increasing precision, document everything we're able to see before it disappears beyond the horizon. We can be the witnesses, the archivists, the keepers of cosmic memory. Not because anyone will thank us, not because future civilizations will appreciate it if any exist, but because the alternative is letting it all slip away unmarked, unrecorded, unmourned. And that feels wrong somehow, like watching a library burn without trying to save any books. So we build our telescopes, we analyze our data, we write our papers and teach our students and pass the knowledge forward. We create a record, an archive, a memory of what the universe looked like during this brief window when everything was still visible. And maybe thousands of years from now, when some future astronomer looks at the meager handful of galaxies still visible from their vantage point, they'll access our records and realize it used to be so much richer, so much more complex, so much more knowable. They'll see what we saw, understand what we understood, and they'll mourn what was lost, even though they never experienced it themselves. That's a kind of immortality, I suppose. Not personal immortality, not the survival of individual consciousness, but the survival of knowledge, of understanding, of the record of what was observed and comprehended during our particular moment in cosmic time. It's not much, but it's something. And in a universe trending toward heat death, toward maximum entropy, toward the erasure of all complexity and structure, preserving knowledge, even temporarily, even in forms that will themselves eventually decay, feels like an act of defiance. We can't beat entropy, can't reverse the arrow of time, can't prevent the universe from expanding into cold darkness. But we can slow the forgetting, document what existed, create islands of memory in the ocean of cosmic amnesia. The universe won't remember, but we will, for as long as we exist. And when we're gone, maybe someone else will pick up the thread, some other civilization, some other form of consciousness, carrying forward the project of observation and understanding. Or maybe not. Maybe we're alone. Maybe when we're gone, the forgetting will be complete. Either way, we do what we can with the time we have. We observe, we measure, we understand, we record, we bear witness to cosmic expansion, to dark energy, to the slow but inexorable increase in cosmic isolation. And we refuse to go quietly, refuse to accept ignorance, refuse to let the universe's strangeness pass unremarked. That's our role, our purpose, if we choose to accept it. Not assigned by the universe. The universe doesn't assign purposes, but chosen by us because we're the kind of beings who need purposes, who create meaning, who refuse to accept that nothing matters. The universe is expanding. Information is being lost. The cosmic horizon is shrinking. And we're here frantically trying to observe everything we can before it disappears. Not because we can stop it, we can't, but because witnessing matters, understanding matters, creating a record matters, at least to us. And we're the only ones here to care, so we care enough for the entire indifferent cosmos. We make it matter by deciding it matters, and then we get to work, building telescopes, analyzing data, developing theories, training the next generation, racing against cosmic expansion, against time itself, against the inevitable heat death that awaits in the incomprehensibly distant future. We won't win, can't win. The universe is too vast, too old, too indifferent to our efforts. But we'll go down swinging. We'll observe and measure and understand as much as we possibly can before the lights go out. And when they do, when the last human looks at the last star from the last remaining outpost of consciousness, they'll know that we tried, that we didn't accept ignorance willingly, that we pushed back against the darkness with everything we had. Not much in cosmic terms, a few centuries of observation, a few millennia if we're lucky, a tiny fraction of the universe's lifespan, but it'll be ours, our contribution, our defiance, our refusal to let the universe's expansion erase us without a fight. The universe is expanding, dark energy is real, heat death awaits, and we're still here, still looking, still wondering, still trying to understand for now, for as long as we can, for as long as consciousness persists and questions remain. That's all we can do. That's everything we can do. And somehow, impossibly, it feels like enough. Claude is AI and can make mistakes. Please double check responses.